All right, welcome back. Something I thought about in the break there that I wanted to mention. I think I got ahead of myself here a little bit. Let me come back to this theorem 2.8 here really in just a moment. You can even leave it where it is in your notes here. Just give yourself just a little bit of space, maybe 1 or 2 lines tops. But more relevant at the moment right now, it makes sense to go in order. Talk about theorem 2.4 really quick. Specifically because this theorem will relate to partitions, which is something we were just discussing earlier. Theorem 2.4 says that the probability of A plus the probability of A complement is equal to 1. And this idea of calculating the probability and its complement and have them add up to 1 is very nice. Because what this means then is that the probability of A is equal to 1 minus the probability of A complement. All right. It's that complementary strategy that we've briefly mentioned before. Sometimes it's really nice. Like, counting an event might be difficult, but counting the complement of that event might be easier. And then you can subtract that from the total sample space. This is the analog, but in a probabilistic sense. The probability of an event might be difficult, but the probability of the complement might be easier. And since the probability of the whole sample space is 1, we can just subtract that from 1 to get the probability of the event we want. And let's just mention why this is. This should be relatively intuitive why the probability of A added to the probability of A complement is equal to 1. That is because, look at 2 things. What is A union A prime going to give you? Well, you're either in A or you're not in A. That's the sample space. And A and A prime are mutually exclusive. These are disjoint events, right? Their intersection is empty by definition of being complements. These are disjoint. They're disjoint, and so what we have here is we have 2 disjoint events whose union is the sample space, so we have a partition. This is like the most trivial partition of a sample space. A single event and its complement. We have a partition of S, and so the probability of A union A prime, because they're disjoint, is the probability of A plus probability of A prime, and because it's a partition, we know that this has to sum to 1 based on corollary 2.3. If it's a partition, the probability sum to 1. This is the simplest partition. I just wanted to mention that there before we moved on to our union of 3 events. All right. Good. Now that we have that, let's get back to where we left off talking about theorem 2.8. What do you do when you have the union of multiple events and they are not necessarily mutually exclusive? You can treat this in a very similar fashion as you could in 2 events, but you just got to be careful to keep track of anything that you're double counting. All right? And so what do we have here? We have the probability of A plus the probability of B plus the probability of C. If you know that these are mutually exclusive, then you're done. But if you don't, or you know that they are not mutually exclusive, then you have to subtract the intersections that you are double counting. We subtract the probability of A intersect B minus the probability of A intersect C minus the probability of B intersect C. However, one can see via a Venn diagram of 3 circles. 3 circles is not too bad, right, to do a Venn diagram on. Right, there's your typical 3-circle region. That's not too bad to do. That when you subtract the paired intersections, you've actually subtracted the triple intersection 1 too many times, and so we have to add that back in. This is our sort of inclusion-exclusion rule, if you will. So when you have 3 things, we're looking at this. And there is a bit of a pattern that you sort of start to see develop. If you look at further results of this, if you look at the union of maybe 4 events, if you will, you're going to have a very similar pattern starting point here where you subtract, you add in the individuals, then you subtract all the pairs of intersections, Then you're going to add in all the triple intersections, but then you're going to subtract out the four-way. And it's going to have this alternating pattern that goes back and forth. Just something to mention. We're not going to really require us in this class to do anything here. That would be a further on level for those math stat major minors who go on to further probability classes. You might run into things like that. Okay, but for us, this is what we're going to be looking at right here. Okay, good. So with these two theorems in mind, I want to do two more examples to close out this section's notes, okay? This first example is continued from the previous airport example we did in the last video, the previous airport example. All right, so let me just scroll back up real quick to that airport example. Right here, page back in your notes. Airport security has 2 checkpoints. Let A be the event the first checkpoint is busy. B is the event the second is busy. We found the probability that at least one of the checkpoints was busy. All right, so same scenario. What are we going to ask ourselves here? The question is, what is the probability that neither checkpoint is busy? Neither checkpoint is busy. What is the probability that neither checkpoint is busy? Neither checkpoint. Well, neither checkpoint is busy. Let's think about that. What is that? Let's think about it. Probably that neither checkpoint is busy. Neither checkpoint is busy. So that would be the probability then that we have neither checkpoint is busy. That's the opposite. Is that not the opposite of at least one being busy? Is that not the complement of probability of A or B? Complement? Right? Well, think about this, right? Think about back to your, so let's see here. Is this equal to, so neither checkpoint is busy. I would say it's pretty clear that neither checkpoint would be A prime intersect B prime, right? Not A and not B. Are these equal? Are these equal? Well, let's take a look at our notes and look at our events. And what do we know about De Morgan's laws is, in fact, they are equal. That's the second De Morgan's law right here. A prime intersect B prime is equal to A union B prime. That's De Morgan's laws. So we can tie that in here. So why do I care about this? Well, these are true. This is true via De Morgan's law. And this is good because we want this. We already know the complement. We know the probability of A or B is equal to, we already know the complement. That's equal to 44%, 0.44. So this is what we want. And so we can get that using theorem 2.4 here, 1 minus the probability of the complement event. 1 minus the complementary event, 0.44, is 0.56. 56% chance. 56% chance. All right. Neither checkpoint is busy. The opposite of that is at least one of them is busy. We know that probability. It's the complement, so we can do 1 minus that. So there's that. And that uses theorem 2.4. All right. The last example we'll do here then is going to use theorem 2.8. Sure, that's not a big surprise to anyone there. I'm going to go ahead and write this out. This one's got a bit of a setup to write down, and then we'll maybe scroll back up so we can look at using that theorem. A survey of a group's viewing habits. A survey of a group's viewing habits over the last year showed the following. showed the following. We have 7 points of interest here, so give ourselves some space. 28% watched gymnastics. Gymnastics. 2. 29% watched baseball. 3. 19% watched soccer. Let's so gymnastics, let's use a capital G there. Baseball, let's use a capital B, and soccer, let's use a capital S on that. Just to shorten this up a little bit. 14%, we have 14 watched gymnastics and baseball. We've got 12% watched baseball and soccer. 6 and 7, and that's it. 10% watched gymnastics and soccer, and 8% watched all three. Find the proportion of the group that watched none of the three sports. That watched none of the three sports. Find the proportion of the group that watched none of the three sports. None of the three sports. None of the three sports. So that would be not gymnastics and not baseball and not soccer, right? None of the three. None of the three. Now, again, we just saw this via De Morgan's law. Similar thing as before. Via De Morgan's law, this is the same thing as, this is the opposite event of gymnastics or baseball or soccer or any of them. The complement of that, right? It's the complement of that event. Gymnastics or baseball or soccer or any combination of those three. You take the opposite of that. That's what we have here. Okay. So why is that useful? Well, we don't know any of these probabilities, but we can find the probability that someone watched at least one of the three. Gymnastics or baseball or soccer, based on using theorem 2.8. Based on using theorem 2.8. So let's do this down here. What is the probability that someone watched gymnastics or baseball or soccer? Well, according to theorem 2.8, it's the sum of the individual proportions. So this is going to be 0.28. That's gymnastics, plus 0.29. That's baseball, plus 0.19 from soccer, minus the pairwise intersections, minus gymnastics and baseball, 0.14, minus baseball and soccer, 0.12, and minus gymnastics and soccer, 0.10. Plus, again, according to theorem 2.8, the triple intersection, add the triple intersection, what proportion watched all three? That would be 0.08. 8% is 0.08. So, adding these numbers up in a calculator carefully, I've got 0.48. There we go. So we want 1 minus that. So about 48% watched at least one of the three. So the opposite of that watched none of the three. So that is a 52%. All right. That'll do it for us in this video here. Please Continue to post your comments, questions in the discussion thread below.